Have you ever wondered how far away galaxies are from us? This question may seem simple, but the answer is a staggering journey into the vastness of the cosmos. You see, the universe is a colossal expanse, so enormous that our minds struggle to comprehend its true scale. The distances we're talking about here aren't measured in miles or kilometers, but in light years, the distance light travels in a year, nearly 6 trillion miles. Understanding these distances, these light years, is crucial for astronomers. It helps them map the universe, understand its structure, and study its history. But you might ask, how do they measure these mind-boggling distances? Well, it's not as simple as pulling out a cosmic tape measure. Instead, astronomers use clever methods that take advantage of the laws of physics and the properties of light. One of these methods is parallax. It's the apparent shift of an object's position when viewed from different points. You've probably noticed this phenomenon yourself when you've seen the scenery shift as you move in a car. Astronomers use this method to measure the distance to nearby stars. Then there are standard candles. These are objects in space like certain types of stars that have a known brightness. By comparing this known brightness with how bright they appear from Earth, astronomers can figure out how far away they are. Lastly, there's redshift. This is a phenomenon where light from an object moving away from us shifts towards the red end of the spectrum. By measuring this redshift, astronomers can estimate the distance to far-off galaxies. All these methods combined create a cosmic ladder of distance measurements, allowing us to peer into the farthest reaches of the universe. These are the tools astronomers use to measure the universe, our universe's tape measure. So, how does this cosmic tape measure work? Let's delve deeper. It's time to embark on a fascinating journey, exploring the ingenious methods astronomers use to measure the distances between galaxies. So, buckle up and prepare for a ride through the cosmos. Imagine holding your thumb up and closing one eye, then switch eyes. Notice how your thumb seems to move. That's parallax. Let's dive deeper into this concept. Parallax is the apparent shift in position of an object when viewed from different perspectives. It's a fundamental principle that astronomers use to measure the distances to nearby stars. Picture this. Our Earth moving around the Sun is akin to you switching eyes. As we orbit, our viewpoint changes, causing nearby stars to seem to shift position against the backdrop of distant stars. But how is this stellar shift measured? The answer is simple: angles. Astronomers measure the angle of this apparent shift. When Earth is on one side of the Sun, they observe a star's position. 6 months later, when Earth is on the opposite side, they observe again. The angle of the star's shift helps determine the distance between us and the star. Now, let's go back to the thumb analogy. The closer your thumb is to your face, the more it appears to jump when you switch eyes. Similarly, the closer a star is to us, the greater its parallax shift. So, by measuring this shift, we can calculate the star's distance from Earth. However, parallax has its limitations. The further away a star is, the smaller its parallax shift, making it incredibly difficult to measure. In fact, beyond a few hundred light years, this method becomes pretty unreliable. Imagine trying to see your thumb move when it's a mile away. That's the kind of precision we're talking about here. To overcome this, astronomers use other methods for more distant objects, which we'll discuss later. But for now, remember this: parallax is our cosmic ruler, a fundamental tool in the cosmic toolbox that allows us to map out our immediate stellar neighborhood. Parallax gives us a starting point, but we need more tools for greater distances. What if you had a light bulb whose brightness you knew exactly? Wouldn't that help you gauge how far it is based on how dim it appears? Now, let's imagine something similar, but on a grander cosmic scale. Welcome to the concept of standard candles in astronomy. A standard candle is an astronomical object that has a known luminosity. Luminosity is the total amount of energy emitted by an object per unit of time. It's like knowing the wattage of a light bulb. If you know how bright a light bulb should be, and you see it dimmer than expected, you can conclude it's far away. One of our most reliable standard candles are called Cepheid variables. These are stars that pulsate in a very specific way. Their brightness changes over time in a predictable pattern. The rate at which they pulsate is directly related to their intrinsic luminosity, so by observing their pulsation rate, astronomers can determine how bright the star truly is. Comparing this true brightness with how dim it appears from Earth allows us to calculate its distance. Another type of standard candle used by astronomers is the Type Ia supernova. These are exploding stars that always reach about the same peak brightness. They are like cosmic fireworks that illuminate the universe, and their consistency makes them ideal for measuring cosmic distances. These supernovae can be seen in distant galaxies, allowing us to measure the distance to galaxies billions of light years away. Both Cepheid variables and Type Ia supernovae have been crucial in our understanding of the universe's size. They've helped us map out the cosmos, giving us a sense of scale and distance in this vast universe. Yet, even with these tools, we're only beginning to grasp the immense distances involved. The universe is a big place after all, but every tool and technique brings us one step closer to understanding our place in this grand cosmic tapestry. With standard candles, we can reach out further into the universe, but we're not quite at the edge yet. Seeing script. Have you noticed how the sound of a passing car changes as it moves away from you? Now imagine that with light. Just as the pitch of a car's horn seems to change as it passes by, light from distant galaxies appears to shift in color as they move away from us. This is what we call the Doppler effect, but applied to light, we refer to it as redshift. So, what exactly is redshift? Well, when a light source moves away from an observer, the light waves from that source get stretched out. They elongate, shifting towards the red end of the light spectrum, which has longer wavelengths. Hence, the term redshift. Now, why is this redshift so important in astronomy? Well, it's because the universe is expanding. This means that most galaxies are moving away from us. The further a galaxy is, the faster it's moving away. This faster movement results in a greater redshift. So, by measuring this redshift, astronomers can determine how fast a galaxy is moving away from us. But how does this help us measure the distance to these galaxies? Well, here's where it gets interesting. In the early 20th century, astronomer Edwin Hubble discovered a relationship between the distance to a galaxy and its redshift. This relationship, known as Hubble's law, states that the more distant a galaxy, the greater its redshift. So, by measuring the redshift of a galaxy's light, astronomers can estimate its distance from us. They use complex mathematical formulas and the constant speed of light to turn this redshift into a measure of distance. So, just as the Doppler effect allows us to perceive a car moving away from us, redshift allows astronomers to perceive the universe's expansion and the movement of galaxies within it. It's like a cosmic Doppler effect, giving us a way to measure the universe on the grandest of scales. Thanks to redshift, we can measure the most distant galaxies in our universe. So, we have our cosmic ruler, light bulbs, and Doppler effect. Together, they form our cosmic distance ladder. Let's take a moment to recap. First, we have our cosmic ruler. This is the parallax method, which uses the apparent shift of nearby stars to measure distance. Next, we have the universe's light bulbs, or standard candles like Cepheid variables and supernovae, which have a known brightness, allowing us to determine how far away they are. Finally, there's the Doppler effect, which uses the red or blue shift of light from distant galaxies to gauge their speed, and thus their distance from us. Each of these methods builds upon the other, creating a ladder that extends further and further into the cosmos. This cosmic distance ladder is an astronomer's essential toolkit. With these tools, astronomers continue to unravel the mysteries of our vast universe, one galaxy at a time.